All right.
There you are.
Recording. Perfect. It says recording. So this is a good thing. So let me share my screen once again because. So I was asking if anyone has any questions related to the first part.
Because I tried to, but I couldn't find anything that I can critique upon. The explanation was so top notch and accurate.
That's good job. So now we're just walk us through the journey. Right?
Hello everyone, once again. Uh, Thank you Abhi for telling us about like the patent Craterhab system, how the things are working in the patent and how the things are working in the real life. Will be going to be telling you the journey about the making the 2 meter prototype. We have done many things with each other, so I will be like discussing that. My section is about what happened when the theory meets real material, real fabrication constraints, and real pressures. This prototype was produced in one attempt. This prototype was not produced in one attempt. Basically, first we have like make many things. For the fabric, first we like testing the fabric. The TPU coated nylon and the PVC comes. Over here, like I want to tell you one thing. We were having two sheets. One sheet was like TPU coated nylon material, the membrane that was like 0.4 mm thick, and second material that was PVC that was the transparent and also was used in the bottom of the base, which was 0.8 millimeter thick. The first membrane which we used to make the dome, in that membrane we have doubled that membrane so we can get a thick and a strong sheet that we have used in dome. The original patent processed advanced materials such as Kevlar and Dynama. These materials provide excellent strength to weight performance, but they were not readily available to us in the locally market, and importing them was a very economical and experimental prototype. We therefore selected two locally available sheets material, each for the different functions. The primary membrane is TPU coated nylon. It replaced with the Kevlar based pressure membrane to the prototype scale. The nylon fabrics provides the woolen reinforcement, while the TPU coating provides air tightness, flexibility, and heat welding. Each TPU nylon sheet approximately is like 0.4 millimeter, which I told you before, and the PVC is like 0.8 millimeters thick, which was like not doubled over there. But the second material, PVC, which is used in the bottom, is like for wrapping, because this PVC material has a little flexibility in it and air tightness. Most importantly, the TPU coated nylon can be thermally bound to itself and the PVC. This allows us to create one continuous joint pressure and envelopes rather than like disconnecting components. Once the material has been selected, the next major challenge was learning how to join them without any leaks. So first we have like trying sewing thing. Sewing would introduce hundreds of needles holes over there, the boundaries and in the edges, like the holes can be leaked very easily. But after that we will think, after that we have decided to weld it. How they weld it? The thermal fusion process for TPU coated surface, because TPU can be bent over with each other. We used an 1800-watt electric heat gun, to heat the overlapping materials, the TPU and TPU coated nylon material and PVC. They both can be melted and welded with each other. We experimented with several processing tools, including jet rollers, and customize our roller as well. In this, we have polished by our team members a cylinder surface which is very smooth and can pressure a very high load on the both fabrics so that they can weld very good without cutting, damaging, and soften the coating. In this time period, we have used parchment paper was placed like between the surfaces where requirement, like when we transfer the heat, does not stick to the TPU, which helps prevents welding tools from damaging the membrane. A metal sheet also was like placed in the beneath the material as it warmed, so it provides heats like from below, allowing the seams from the receiving from uniform thermal energy from both sides. So it can be like very much better. The process was like extremely sensitive in this era. Okay, proving the fabric this time we were like testing that how much the fabric is sustainable for this project. So before constructing a complete dome, we need to like answer few like questions over here. So like first question, can this material is like weld enough and like can withstand this pressure, that the high pressure which we are going to be getting in like in the higher scale. To answer that safely and economically, we cut small samples and the fabric pillows shaped pressure vessels. So these pillows were very helpful in our like journey. Let me tell you one of our samples. When we once we have like early samples were like repeatedly leaked. The problems were including there was like pinholes, incomplete fusion, wrinkles in the edges, and inconsistent like overlaps, and the width was like not matching with the calculations. Each failure helped us like refining the temperature, pressing, force, welding shape, and like joint geometry. And the geometry was the basic over here, no? One like big problem. Our final pillow was tested was like pressurized toward a target at a 3 bar, but we failed at approximately at like 2.7 bar, with the failure developing a weak joint rather than through the undamaged central fabric. This gave us one of the most important engineering lessons, that the entire project, the strongest material is only as strong as its weakest seam. Where the like high temperature was like seemed, so there was like a weakness of the like our material. So this was told us to like doubling the layer so it can become more stretchable and flexible, not flexible, more stretchable, and can sustain the higher pressure in the like long run. As a resultant, we like construct this whole prototype with this. Now I want to tell you about the prototype of 1 meter, which tells us very unique thing, that geometry is something which we have to be understanding in a start. Okay. Its purpose was not to be like reproducing final Craterhab structure. Its purpose was like to be proving the welding membrane envelopes the codes, remains pressures, and shows us like geometry behaved during inflation. The prototype used a combination of hexagon and pentagon panels over an internal metal frame. This concept has been changed in 2 meter. I would be like telling you in other slides. As the dome inflated, the pentagon section increased the angular closure. The surface gaps were like more thicker, open between these panels. Like the gaps were not easy to be like joining because the size wasn't that much big to be comfortably working over there. Okay, and the shape after when it was inflated, the shape was like become a higher in the height, and it was like a football type shape. So it wasn't on our like basis of like which we have to be like in the patent, as Mr. Abeer has said to you, that the things have to be working. This experiment demonstrated the air pressure does not independently determine the final form. The panel arrangements, edges, dimensions, boundaries, conditions, and supporting frames all controls the membrane expands. The key lesson over here, which we have learned in this prototype, was the main thing. The geometry controls the final shape as much as the air pressure does. Next slide. Okay. Now the 2 meter prototype was like the most uh, what we can say passionate thing in the all time. With this material process have proven and the geometrically problems understand, we defined the final 2 meter prototype. Its purpose was different from the 1 meter model. The 1 meter model mainly tested the welding pressures and envelopes. The 2 meter prototype was designed as a test integrated structure of 2 meter prototype. It has an effective radius in this 2 meter. The effective radius of the is 1 meter, and the width was of the 2 meter of the diameter. The main pressure membrane is double layered. The TPU was the nylon sheet was doubled over here because we can get that much strength in the fabric because we have already burst it once in the pillow. So we have learned over here. Another thing, like an external 16-meter braided nylon rope was used as a skeleton of the dome, which can hold the pressure because the pressure inside is too much higher that it can easily burst because the material was enough strong, but there was a pressure which was very high. Okay, the basic interface consists of two constant rings. We have make two rings in the base. The membrane is sealed at the interface through the torus anchor containing the dual cotyledonal tube system. This system I will be telling you in few next slides. This design tested pressure plus 0.4 bar gauge equivalent to 1.4 bar absolute. This prototype does not reproduce every component of the full patent. Instead, it reproduces the essential structural sequence. Pressure enters the membrane develops the tension in the rope in the skeleton, control the distribution of the tension, the rings in the sealing system, transfer the force in the prototype, and supports our structure as well. The next slide. Okay. Now it was the time to be redesigning our Craterhab, the 2 meter Craterhab. Now all the facts, all the figures are in our hand, and now we are going to be working on our final prototype. We shifted to hexagonal dominating panels. First, we were working on the panels which were hexagon and pentagon, but now we are shifted into the hexagonal dominating panels pattern because hexagon provides 6 neighboring load sharing, shorter unsupported membrane span, and direct alignment with the external rope of the skeleton which is used on the dome outside that. Near the base, perfectly regular hexagons could not fit circularly boundaries. We therefore used very carefully edges and trimmed boundary cells. Precise cutting was critical over here because a small dimension error in one panel does not remain isolated. It affects nearby other panels, seams changes into the curvature, and the wrinkles can come over here in the edges and uneven force distributions during inflation. So this was the precise calculation, and the cutting is what the one of the most important work. At this base, we designed a dual steel ring system to represent the future crater rim. The ring was installed on the adjustable PVC pipes, so we can use to adjust in future that how the structure can be changed as our things. Next slide, maybe. Okay, now the dual steel, the ring which we have make for the Craterhab interface. So let me tell you small calculations over here.
Maybe you can
Or maybe
Yeah.
Farrukh can cover this.
So, we are short of time. So these are all the calculations of the stand and the structure, I think. So let's quickly skim through this, right? So we have the steel ring stand. Then there was, you can quickly tell about cross anchoring coordinate.
Like I want to tell you a small things about the cotyledon seal tubes. In this, like the primary ropes has been from the two tubes, which is like continuing downwards towards the counterweights. So these continental tubes have the friction between those ropes, which easily cannot be easily escaped from that part. And these cotyledon tubes works on the PVC, and like the membrane of the both membranes was stuck with each other. So this the pressures becomes the compressing and the seed membrane without applying a sharp local pressure that rejects metal clamp and to like could create a grip over there. Okay, now the one of the most important thing, which is like a nylon rope skeleton, which we have like make for the dome. In this, like we have used 16-meter braided nylon rope. There was like primarily 12 vertical ropes edges or like ends, which is like stopping or holding a weight over there so it cannot move outward. The angular spacing was like of like 30-degree over there, and this is like working on the dome external dome hexagons at that shape. This is also is like working over there. Okay, now there was a small thing I want to tell you about the 2 meter prototype. As when we assemble and inflated the 2 meter prototype, so there was like one one thing which was like we cannot observe in the small. First we have used pumps, and then is after we have arranged the bigger pump, which was like 10 uh 10 times powerful than the small pumps. So after that, we got to know that there was a condensation. There was two problems we are getting, that there was a condensation in the dome because of a high pressure. And one more thing we have understanding that there we don't need the high pressure over here. We need the larger amount of air blower. So first in the tank, first in the like tank of which we have used over here. So there's very less low flow, airflow. But because of the pressure, we used to need like in the end. But because of the maintaining this dome, like what we can say a bowl or a half full wall, so we need a air blower which can fully like inflate that dome in a minute. The high flow at low pressure, no cooling. This makes us like first we have like used a high pressure, so we have found there is a like a pool of little water over there in the inside the dome, and we have used the PVC as because of so we can see the things which are happening really inside the dome. So this is the one of the reason that we need a higher airflow rather than the higher pressure in this dome to be like inflating these big structures. Uh, Thank you thank you for giving me your time, precious time. I want to continue, Farooq.
Thank you, Dawar. Are there any
Thank you,
questions?
Dawar. That was very good.
If there are any, confusions, then I can clear that up as well before we move on to the data part of the presentation.
So I think that the condensation from the compressor was because a very high pressure air was coming out of the nozzle into a very low pressure environment comparatively. And was it causing condensation?
Yeah. So what was happening actually? So we actually used a very high grade compressor, which was actually operating at around 10 bars pressure inside its metallic tank. But the pipe that is coming out from that tank was a very narrow pipe, and because of that, the flow was actually not much, which means that a lot of pressure was there, but not a lot of airflow. That pressurized air, when entered into the dome, it expand. It expands so much because the pressure inside the dome was way lower than 10 bar, and that was actually causing the condensation. Because whenever the air uh, is uncompressed, it will actually cause condensation. So that was
That's the
resulting in creation of some water inside the dome, and it was actually accumulated at the bottom part, which we could see through the transparent bottom part of the dome that we actually created through PVC. But it was then replaced by high throughput, high airflow blower rather than a compressor. So we used a blower to actually fill a lot of air within a minute. Actually, it was filling the whole dome. I think in like uh, 50 seconds or something, or less maybe. But it wasn't causing any sort of condensation inside because the pressure was not high. I hope that answers. Are you guys able to hear us?
Mm.
Are we connected or
Yes.
not connected?
Yes, we can hear you.
Okay, cool. I was just wondering whether we are still connected or not. Okay, so Akbar, Raul, Alejandro, are you guys able to hear me?
Yes, yes, of course.
Okay, cool, cool. So you could listen to the answer that I gave about the condensation thing, right?
Yeah,
what
yeah, yeah,
answer?
yeah, yeah.
No, we were. I think. Yeah, no, we did. I'm just joking. Yeah, you haven't paused at any
I,
point.
I should not just repeat everything again.
No, absolutely not. Okay.
Okay, so over to Farrukh. If there are any other questions.
Oh, no, no, not from my side. Much appreciated with the presentation. Everyone made a great explanation about the difficulties that you were finding from in translating from the 1 meter to the 2 meter. I think that clarifies a lot of learnings, pointing to building up a new prototype. There is a lot of learning in building up the 2 meter prototypes. I was capturing the difficulties of engineering the model, the first model, um, by welding the hexagons, by welding the pentagons, and how does the assembles resist the higher pressures in between. Then certainly there is a lot of learnings that will help us mostly with the application for the governmental funding here in Chile for the Latin American models. It is important for us collect all these learnings because the sooner the better we will need to reproduce what you have done there. Will be forced to reproduce here locally for several reasons. Because it is a must demanded from the authorities in order to approve the project for government funding. And the approval for government funding is basics for for attracting investors here in this region. The investors, even their angel investors, they take care of the approval of governmental institutions. So the governmental institutions requires to make a protocol to reproduce these kinds of research and prototypes. So all your learnings, as soon as you describe step by step, and make a protocol, a procedure to build up based on those learnings you explain, will help us to get those approvals from the government here in Chile.
This is great. Good to hear about that. And yes, that is definitely going to be the path forward. So yeah, move on to Farrukh for sharing about the data results and what's the next steps.
Thank you,
Excellent.
Dawar. So thank you, Dawar, for sharing our incredible journey of Craterhab from a pillow to a 2 meter dome. So we have now seen the complete development journey from the material selection and welding trials to the assembled and pressurized 2 meter prototype. My sections addresses the questions follows to once the pressures enters the structure, where do the forces go and how large are they and what do they tell the about prototype. So I will explain the pressure loads, the response of the membrane and foundation, the circulated margins of the ring and bolts rope system, our pressurization method, what we have genuinely validated, and the next pathway towards a measurable and certified pressure rating. So uh,
Nope, nope,
no,
it's
okay.
working.
So, uh, so comes to the first thing I want to discuss that the pressure loads on our dome. So the first result is fundamental. Uplift is determined by pressure and projected area, not by the material selected for the membrane. So our prototype has an effective sealing radius of 1 meter. Its projected circular area is therefore approximately 3.14 square meter. At a gauge pressure of plus 0.4 bar, the pressure difference across the membrane is 40,000 pascals. So when we multiply this pressure by the projected area, the total vertical uplift becomes approximately 126 kilonewton force. So in more intuitive terms, that is approximately 12.8 tons force, uh, attempting to lift 2 meter dome away from its base. This results demonstrate something that may not be visually obvious. Even modest pressure acting over a relatively small area produces a very large structural force. That uplift is not resisted by one component. It is shared through the membrane and the rope network, the cotyledon interface, the steel rings and the bolts, the external restraint system. The dome looks lightweight, but pressure makes it structurally heavy. So the next, as we know that the Newton's third law state that the every action has an equal reaction. So the pressure pushing upward of the on the dome also pushes downward. So the flat base has the same projected area of approximately 12.3.14 square meter at plus 0 0.4 bar gauge pressure. The downward force is therefore also approximately 126 kilonewton force or 12.8 tons force. So during the test, the base membrane didn't remain perfectly flat. Uh, it it bored downward into a shallow pressure supported shape. This deformation transferred the load into the temporary PVC pipe foundation. The pipes eventually buckled because the portable stand was designed for assembly, access, and observation, not to behave like a massive crater floor or reinforced foundation. So this should not be understood only as a failed support component. It was a valuable structural result. It physically demonstrated why it is why the patented Craterhab depends on the natural crater, reinforced concrete, underground anchors, and the mm, surrounding soil or regolith. So in the final concept, the ground becomes a part of the structure and observes these reactions force directly. So the prototype therefore showed that the pressure membrane can be lightweighted, but its foundation can't be treated as structurally insignificant. So the comes to the next slide, the membrane. So comes to the next slide, the membrane stress for a single layer or double layer. So we next evaluated the nominal membrane stress using the thin spherical membrane relationship at a pressure difference of 40,000 pascals, a radius of 1 meter, and the thickness used in our calculation. The nominal stress is approximately 25 megapascal for a single structural layers. But if two layers share the load equally, the nominal stress becomes 12.8 megapascals per layer. So the assumed tensile strength range of the tubio-coated nylon is approximately 40 to 60 megapascal. So using the conservative lower value, a single layer would operate at approximately 62% utilization. With two layers sharing the force, the nominal utilization drops to approximately 30%. However, the calculation describes the general membranes fields. It doesn't automatically prove the capacity of every welded seam, panel corner, valve opening, fold, or rope contact point. The final pressure limits will therefore not be determined only by the strength of the intact sheet. It will be determined by the strength of the complete fabricated envelope. So the material carries the pressure, but the seams decide how much the pressure the structure can actually keep. So the next slides shows that the steel rings and the bolts. So the steel ring system resists the outward circumferential pull developed at the base of the membrane at plus zero point 0.4 bar. The simplified ring line load is approximately 40,000 newtons per meter. So multiplying this by the circumference of approximately 6.28 meters gave us a total circumferential load of about 250 kilonewtons. So under our analytical assumptions, the corresponding average stress in the steel ring is approximately 35.7 megapascals. The ring material is S2275 structural steel with a nominal yield strength of 275 megapascals. This gives a calculated ring utilization of approximately 13%. The two rings are connected using a 32 M10 grade 8.8 bolts. Under an ideal equal load distribution, each bolt carries approximately 7.8 kilonewtons compared with an assumed shear capacity of approximately 30 kilonewtons force. So
That
yes,
means that the stress on the outer ring is 25 tons, and each bolt is carrying 780 kilograms or equivalent of weight. Now that is very significant because this is exactly why I don't want any metal parts above the surface. So the design of the Craterhab is that there should not be any metal parts above the ground. So it's all fabric, because even in the prototype, I see that if there was any rapid. If there was any breakage, things would fly out at very high speed. So yeah, I think for the next model we should be following the patent um guidelines of burying everything under the ground, and only the fabric structure should be above the ground. So this result is very, very significant.
Yes, exactly. In our patented design, we know that we don't have a base structure, that we use a ring system. We have a ring system, but for the cotyledon and torus anchors, Craterhab system for its pneumatic sealing. So we will use the other concept. Just is this bolts pressure distribution, force distribution is just only for the our 2 meter prototype. What we have done before. So, should I continue?
Yes, please carry
Yeah.
on.
Thank you. So, comes to the bolts. Under this, that gives a calculated bolt utilization of approximately 26%. These results indicates the steel rings and the bolting system operates well below their assumed material capacities at the design pressure. However, future testing should still measure actual ring ovalization, bolt preload, and local bending, because real structure don't distribute forces perfectly. So the steel system has a wide calculated margin. The rope skeleton operates closer to its selected capacity. So comes to the next slide. The rope skeleton, the load check at our surplus 0.4 bar. So the external skeleton includes 12 primary vertical ropes distributed at 30-degree intervals under the simplified assumption that the 126 kilonewton uplift is shared equally. Each primary rope carries approximately 10.5 kilonewton force. So when we apply a safety factor of 3, this gives a required minimum breaking load of approximately 31.5 kilonewtons per rope. So the selected 16 millimeter braided nylon rope has an assumed breaking strength range of approximately 35 to 40 kilonewtons force. So it is stated the capacity therefore exceeds the calculated requirement of for controlled prototype validation. However, this is the current narrowest major calculated margin in the structure. So the actual rope capacity may be reduced by knots, splices, tight bands, and around knots, abrasion, and an unequal rope length, cyclic loading, and the long-term creep. This means that the future validation shouldn't test the rope alone. It should test the complete rope and the knot assembly. So comes to the next slide. Uh, we now we discussed the structural utilization at our surplus pressure bar. So this chart brings the main structural calculation together at the 0.4 bar. The double layer membrane is approximately 30% utilized, and the steel rings is approximately 13% utilized, and the bolts are approximately 26%, and the rope skeleton is approximately 84% utilized against the selected safety factor requirement. Every calculated component remains below its assumed capacity, but the margins are not equal. The steel rings have a wide margin, while the rope system is much closer to the design requirement. In addition, welded seams are not represented by a simple material utilization percentage on this chart. And based on our flow test and fabrication experience, seam quality is likely to be governed the practical pressure sealing before the intact steel components too. Therefore, the most technically accurate conclusion is the rings, bolts, and the nominal membrane field remain below their assumed capacity, while rope connections and welded seams remain the critical validation area. So the strongest component doesn't define the system. The weakest verified connection does. So now comes to the next. This
Alejandro has a question, so I think we will let him ask before we move on. And I have a question as well.
Yeah.
Yes, yes, yes. But can you get back to two slides, please? There you are. The rope skeleton, is connected by knots and rope extensions, right? And those knots and rope extensions achieves the shapes or should copy the shape of the hexagons approximately, perhaps distributed in triangles. But the load distribution for the rope, it depends on the knot tightening and the rope extensions. So it might be distributed unevenly around the dome. That means it might be have points of weakening, and some other points are more strength distributed. Have you evaluated the variation in the resistance around the whole skeleton for those measures that you're showing there?
So,
Did you capture the question? Yeah, thank you.
Yeah, this is a great question. So we have there are at least three different things that has to be answered in this one. One is the I would say symmetrical hexagons, right? So definitely in a smaller structure, the unevenness in the geometry, that's a calculated geometry, not because of some error. In a smaller structure, this unevenness will be bigger. In a bigger structure, they will start to become more uniform, right? So this is one thing to consider. But however, these all are symmetrical. I mean, if you travel from the top to the sides, from the middle to the sides, the unevenness is actually symmetrical, which means that the load distribution from the center to the sides, because this is how the force elements are traveling, because eventually the force ends up at the base, right? So we say that the internal force which is applied on the fabric is transmitted to the skeletal framework, which is created by these ropes, and it travels down towards the side to the base, and then it ends up into the torus anchor, and then it goes beneath when we actually will be deploying it on the ground. So this is one thing. Second thing is the knots and which we talked about. So knots will actually distribute it three ways, of course, because every knot has the other. Sorry, not three ways, the two ways, because the force is traveling on one rope and it then transmits into the two other ropes and eventually ends up in the 12 single ropes, which are then tied up or actually passing through the torus anchor. But they are all symmetrical. I mean, they can be
Okay.
some non-uniformity because of certain, I would say, practical errors, but by design they are all symmetrical, which means that, and they are all symmetrical and they're all equidistant, so they will actually distribute the force equally at the base, and then finally all this will be going through the bottom part where we actually have to hold the ropes at the bottom. So for that, when we pressurized it, we actually had to apply some very heavy weights to all those 12 ropes, so that, because as um, Farrukh mentioned, that there was a huge total uplift that has to be countered by those counterweights. Uh, So it was through the counterweights as well as the steel rings and the friction in the torus anchor. It was all managed through all these three things. So the forces that Farrukh has mentioned actually is about the same. First, he has told how the total force was, uplift force was, and then he's talking about these force distributed through the rope skeleton, and then the same force actually goes to the steel structure, which will be absent, actually not absent, will be replaced by the concrete structure underground, which will be created. But right now, in this 2 meter prototype, that was there, that actually was transmitted to the steel structure. So the next slide actually had that, well, not the slide, but this one was that. So does that answer your question, Alejandro?
No, not from now, but I'm okay with that explanation. Thank you for that, Mehdi.
Okay.
I just have to add one more thing is that because we are keeping a 2.5, at least 2.5 times safety factor. So overdoing the engineering will also absorb some of the discrepancies and the structural stress unevenness.
So I guess, Alejandro, you meant to ask that for every knot and every rope segment, is
Yep.
there a measure of force for each one of them and is captured somewhere? Is that what your question was?
Yeah. Because as soon as depends on the type of the knot and the location, the position of the knot in between the triangle or the pentagon that you are forming, it might be unevenly distributed the forces, but as you explained, and it clarifies to me that the force is redistributed along the whole skeleton evenly. So it clarifies to me what Farrukh was explaining at the beginning.
Okay, perfect.
Thank you.
So we'll
Thank
have
you.
some more data. We'll have some more data and we'll share those with you, which might help even more in explaining the same. Akbar, did you have any question as well?
No. No, actually, I had one question. Yes, if you go back onto that bar chart, horizontal bar chart.
This one?
Yes, so we see that all the key components they have a lot of safety factor. Was there any, and as Farooq mentioned, and as we know in engineering, is that a chain is as strong as its weakest link, and this principle in engineering is even more paramount in aviation and space engineering. So, is there any key component that was very close to its breaking point? Because we need to meet this 2.5 times safety factor in all circumstances in every core component.
Yes. Yes, we have one weakest link here. As you can see, that same safety factor we could not achieve in the rope skeleton, but we know that the rope that we have used in this is actually already a downscaled version of what we'll actually use in the real Craterhabs and what's mentioned in the patent as well. So we have used, the double braided nylon rope, which actually can be made even stronger. The stronger ropes are also available, but what we have used, we know that we could actually use stronger ropes, or we can go to the Dynama cables as well. But we that was the weakest of all. If you can see here, it's 84% utilized. The strength was utilized, while the other were actually even less than the 1/3 of what they can, or the membrane was actually only 1/3 of its strength was utilized. It can actually be a 3 times more. Well, steel ring, well, that was actually not the real part. It was just meant for the 2 meter prototype. But yeah, that was also way much underutilized at this point. This actually gives us how the forces would be when we create a concrete structure and we put the helical anchors in it, we through this we can actually know what sort of forces will be applied on those, and for that what sort of structure we need. So steel link can actually tell us a lot about that as well. But yeah, the weakest link is the rope skeleton.
All right, thank you. Yeah, let's move on.
Yeah, sure.
So back to the topic, the main protocol we need to follow when we create Craterhab. So the pressurization protocol, because the prototype stores significant mechanical energy, pressurization must be gradual and controlled. We begin with a complete pre-test inspection. We check the welded seams, ring bolts, rope alignment, and cotyledon position, valves, gauge, and the pressure release path. The dome is initially raised to plus zero point 0.1 bar and held for 5 to 10 minutes. During this stage, we observe the symmetry, the panel deployment, uh, rope balance, and a seal behavior. Pressure is then increased through controlled stages, plus 0.15, then 0.20, then 0.25, then last 0.30 bar. At every stage, the system is paused and inspected. At approximately plus 0.25 to 0.30 bar, the cotyledon tubes are progressively engaged to stabilize the sealing interface. The dome is then raised to the design test condition of plus zero point 0.4 bar, equivalent to 1.4 bar absolute, and held for it for at least 60 minutes. So during the hold, we monitor leakage, membrane deformation, rope symmetry, a ring displacement, and the seal stability. The complete validation sequence is pressurize, stabilize, isolate, and the major pressure decay. This is what the separates the visual inflation demonstration from an engineering pressure test. So the next thing is that the pressure difference with absolute pressure and the gauge pressure. This slide clarifies the pressure referencing used in the prototype. The surrounding atmospheric pressure is approximately 1 bar absolute. This is our external baseline. The cotyledon or torus seal was held at approximately 1.05 bar absolute, or relative to the surroundings atmosphere, that is only about plus 0.05 bar gauge. This small pressure difference was enough to seat and grip the membrane at the ring interface without excessive compression. Inside the main dome, the peak condition was 1.4 bar absolute, when the outside atmospheric pressure of approximately 1 bar is subtracted, the structural pressure difference becomes plus zero point 0.4 bar gauge. That plus zero point 0.4 bar differential is the value responsible for the 126 kilonewton uplift. So when we say 1.4 bar inside the dome and plus 0.4 bar gauge, we are describing the same operating state for from two different referencing points. So in other words, absolute pressure describes the air, but the gauge pressure also describes what the structure feels. So the next slides uh, comes to our 3D model to cutting workflow. Repeatability was one of the main objectives of our geometry works. We didn't want the 2 meter prototype to remain a one-time handmade structure. We wanted a process that could be repeated whenever the diameter, height, or curvature changes. The workflow begins by defining the dome diameter and the required rise. A geodesic triangular mesh is then created and projected onto the intended curved surface. The mesh is converted into its dual network, producing mainly hexagonal cells with the necessary pentagonal or boundary correction. So every node is projected onto the three-dimensional dome. Each panel edge and rope segment is measured and assigned an unique number. These dimensions are exported into a cutting assembly schedule. For any two nodes, we distinguish between the straight chord line used for a tension segment and the arc line they use when the following curve membrane surface. This workflow allows the dome to be reproduced instead of manually approximated. So it also ensures that whenever the scale changes the panel geometry, the rope length, membrane forces, and total uplift are recalculated together. So the the major thing we need to discuss here, what the our prototypes claims and validates. So we must define our technical claims carefully. The prototype validates that a semicircular dome can be formed from segmented TPU coated nylon panels. It validates hexagonal membrane construction methods, and it also validates the rope assisted tensile load sharing. It validates the cotyledon-based pneumatic sealing concept. It validates the use of dual steel ring as a temporary substitute for the crater interface. And at last, it also validates the control inflation, the fundamental load part from the pressure through the membrane and ropes into the ring or support system. So, however, it doesn't claim the full pressure rating, the patented Kevlar Dyneema structure. It doesn't establish full scale planetary suitability, and it doesn't represent a human rated or certified pressure habitat, and it doesn't yet establish the final pressure ceiling of the prototype. So those claims requires certified material data and seam testing rope and node testing, pressure decay measurements, cyclic loadings, environmental exposure, and independent validation. So the so the in this slides we discussed the physics, what our prototype deals. Although the long-term vision is planetary habitation, the same pressure structure physics has immediate terrestrial relevance. At high altitude, reduced atmospheric pressure lowers the available oxygen pressure. This affects the sleep, recovery, cognitive performance, and long-term health, particularly for mining teams operating in the Andes. A controlled Craterhab structure could provide pressurized sleeping areas, recovery spaces, or emergency refuge modules for high altitude workers. Similar systems could support climbers, trekkers, tourists, remote researchers, and technical crews. So these applications create a practical bridge between Earth and Mars. Terrestrial deployment can generate operational value today while providing data on air tightness, pressure control, energy consumption, safety system, material durability, and long-term performance. In this way, Earth application don't replace planetary vision; they accelerate it. So comes to the next slide, and this is our TRL4 prototype from our patented Craterhab technology. So we are currently describe the 2-meter system as a TRL4 prototype. The major components have been integrated and tested in a controlled environment, experimental environment. The next stage is laboratory characterization. We need a verified warp and weft strength of the membrane, seam efficiency, tear resistance, coating adhesion, uh, rope minimum breaking load, and the node reduction factors. So after material characterization, the complete structure should undergo instrumented testing. This includes pressure decay testing, cycling inflation and deflation, fatigue trials, rope-based monitoring, membrane strain measurements, and a ring deflection remeasurement. The following stage is a scale up. A larger prototype should use a concrete or ground-supported rim that reproduces that stiffness and the reaction path of the patented crater interface more accurately. The underlying physics doesn't need to be reinvented at every stage. What must improve is the quality of the evidence supporting each energy engineering claim. So the next comes to our Mars vision. Uh, this is the long-term vision behind the technology. On Mars, natural craters could provide the lower structural boundary of large pressurized settlements. Lightweight tensile domes would enclose living spaces, greenhouses, operational areas, and connected habitat modules. The concept reduces the amount of rigid structure that must be transported and uses the existing terrain as part of the habitat. The ultimate goal is not only to create a temporary shelter, is to create a low cost, scalable, and permanent human settlement beyond Earth. Our 2-meter prototype is a very small physical step, but it tests the same essential load part required by that much larger vision. So on Earth, the terrestrial vision can be developed much sooner. In the Andes, Craterhab units could be deployed individually or in clusters near high altitude mining sites. They could support sleeping, recovery, refuge, and uh, controlled environmental functions for personnel exposed to chronic hypoxia. So, so the Uh, uh, so the next is our theory converted into a working structure. So to conclude this project with a patented vision and the progressed through practical engineering, we transform the original material system into a locally available alternatives. We developed a repeatable hexagonal geometry. We established a thermal welding process. Uh, we tested pressure retention through small samples. We developed the torus and cotyledon scaling interface. We integrated the membrane, rope skeleton, steel rings, base, and inflation system into a working 2-meter prototype. And we successfully observed how pressure moves through the through the complete structure. The central physical principle remained unchanged. Internal pressure becomes membrane tension. Membrane tension is distributed through the hexagonal rope skeleton. The cotyledon system seals and grips the interface, and the resulting force are transferred into the ring and the foundation. So this prototype is not the final crater have. It is something essential before the final system can exist, a working experimental bridge between the patented theory and measurable engineering reality. Our complete journey can be summarized as the patent, physics, materials, geometry, build, and the data. So this is the line which reflects our complete journey. So thank you for your time and giving us the opportunity to present our journey when we uh, make this prototype from to pillow to 2-meter dome.
Thank you so much, Farrukh. So that this concludes the presentation, though it's a very long one, and I guess it just
Yay.
went above the schedule timings as well. Let me just share, and if anyone has any questions related to that, so we can, go over those. And any other comments are welcome as well.
Yeah, we just welcome Dr. Nazair. He joined during the presentation, so I hope you got some of the material shared by them and got some insight into the prototype construction.
Yeah, thank you very much. Indeed, this is really excellent work. Congratulations on to Mehdi and your team and all engineers from Pakistan. Maybe, of course, this is going to be recorded and then you will share with us more data and the results as Alejandro would also like to have. I have just a very general couple of questions. One is that if I missed, for that, excuse me in advance, but the conditions related to the temperature, when you talk about ideal gas law, PV is equal to nRT. So the question is that what temperature would you consider and what is the range of the temperature that we can consider that can coordinate with the pressure infusion? And then this is one thing. And from Alessandro and Raul perspective, of course, this prototype is envisioned with the high latitude mining areas. Then how much we can relate those temperature conditions in connection with the pressure that we are going to develop with the actual Mars craters or the surface. So this is one thing. The second thing, again, apart from high latitude mining prototype that we would like to present to certain investors, regarding the Mars, we might have a lot of charged dust there. So my question is that, as Dr. Akbar already mentioned, that nuts and bolts should not be exposed there, and they should be covered by the fabrics. And one of the reasons could be the charged dust storm to the low surface latitude at Martian surface. I'm not sure about the craters, that what would be the state of these charged dust particles there, but at least through the flat surfaces, we can expect that they are hopping around from one place to another. So I'm just thinking, fetching not only the high latitude mining idea, but also connecting with Mars, which is the eventual, purpose for us. So these are the two comments that I would like to float in here.
Very valid and great questions, of course. Thank you for those. First question is related to the temperature conditions. So usually when we talk about PV is equal to nRT, we say that whenever we pressurize something, the pressure goes up, right? But we talk about that when we have a system that does not conduct the heat to the rest of the system, if it's just this one system we are talking about. But here, when we talk about Craterhab, there is no thermal isolation. The temperatures and heat transfer is something that we are not right now considering as a constraint. Rather, we will actually control the temperature inside of the dome separately, which means that when we pressurize it, the temperature will go up. But it's not a sustained temperature at that point. If we are not thinking about a controlled environment, the temperature will automatically balance with the rest of the environment outside the dome. That is why when we pressurize the dome, the temperature didn't go up. We had the temperature sensor. We had the temperature sensor, right? Yeah, it has a humidifier, humidity measure, and the thermal. So we actually had that placed inside. That is for the inside gauge. So this one actually tells So it's a small one that can be, pushed inside and we attach it the inside of the transparent part, the PVC part of the dome, and it showed the humidity and as well as the temperature. So it does go up slightly, but then it comes back to the same as outside because the pressurized environment. So if it blasts, then the temperature of the surrounding, the close surrounding, goes down actually. But during the pressurization, it goes up, but then it transmits the heat. Is exchanged with the environment. It becomes the same, unless we have a controlled temperature controlling environment that actually for air conditioning or a heater system that creates the temperature that we desire inside the dome. This is a separate thing. So one instance when we had actually created a big pillow with that fabric, it burst. And when it burst, something that we have not thought about happened. There was a white cloud that emerged out of it. And we were not able, that was for an instant only, but we were amazed to see what was that? Some ghost or something that just came out of it, or what?
There's a movie Mist, when they create a portal into some other dimension and these monsters come out. I said, don't create a portal.
So it was like a white cloud that came out, and then later we realized what exactly happened was a sudden condensation because the pressure inside the dome was close to like 2.5 bar, and when it exploded, it just expanded suddenly. The air expanded suddenly, and it caused the condensation. But before bursting, it was at a normal temperature, right? I'm sure that when we were actually inflating, it went up, but we were doing it slowly. So it was also doing the heat exchange through the fabric, and it was not going too high. But when it burst, the whole air suddenly just expanded, and it created the condensation, which actually created that white cloud, and then it just disappeared. So that was related to
just the point to be noted. Of course, this explanation is you answered this, but maybe I will forget. So that's why I'm just quoting it here. That which air are you using to inflate? It is clean air or it is normal air?
So it is normal air. I mean, we do not have a chamber with some, sophisticated air quality control. Right now, it's a normal lab that you see here.
So just for the future, when we will present to the companies or so on and so forth, of course, this is just right now the prototype of the prototypes, right? So this is one of the points that I wanted to highlight in future. And the second one is that the blast is really an issue, right? The Zisher height, we say it here, Ayaz can relate to that. Security measures that we need to do that. Are you placing also somehow the rupture disk somewhere in this dome so that whenever this blast event could occur, it should only occur to the minuscule level so that there should not be any damage and then...
So here's the thing. That pillow that we actually created was made up of a single piece. But you see that this is exactly what was told during the presentation, that we actually then created the dome through small segments, and they were joined together with the rest of the fabric material, right? Which means that only in case it blasts, though we actually tested it at 2.5 bar with a single layer of TPU so that we can understand what the strength of a single layer TPU coated nylon was. We actually then created it with smaller segments. So in case it blasts for any reason, only a small portion of it gets away, and that will actually result in two things. So that was also something that we understood, that we actually created a hole in in our 2 meter prototype as well, through which we actually inserted the blower. When we actually uh, separated the blower out, the dome didn't suddenly collapse because the hole has a capacity to actually move the air out of it.
Kind of
And
back pressure, and then stopper kind of thing.
right, and no, I'm telling you that even a small hole of this size, when the dome is really big, right? It took a while to actually the air to get out of it, even if the dome was highly pressurized, right? So if we consider a fact that if there's a large dome which was actually made up of small pieces, if an unfortunate event happens and some part actually explodes or give way, it is still won't explode. It will actually start leaking, and it might take a lot of time for the air to actually drop its pressure inside the dome. Think about a tire, the tire tube or tire of a car. When I don't know if you have deflated it. We do off-roading, so we deflate it usually. It takes some time for us to actually deflate it to a level where we can, drive on the sand and rocks. So yes, it won't explode completely. Even in certain cases, if there is an issue, then it might be just a small segment that will get away. And if we talk about like 50, 100 meters or more than 100 meters dome, I'm sure that it will take a lot of time in such an event where we can have some, emergency pods inside where people can go and, take refuge as well in such cases.
What Dr. Nazar is saying is that, and that's what we have the intention, that one of the hexagons out of all these tens or hundreds of hexagons, one hexagon would be made just a tiny bit weaker, maybe like 10% weaker, even though the safety factor would be 2.5x.
Oh
The
yeah,
way,
yeah.
so
Yeah.
even then, only that part explodes and then decompresses the whole system, so that there shouldn't be any ripping event, and that will also be protective to protect any sudden decompression of the.
Yes,
Oh,
exactly.
sorry, I didn't get it wrong. I didn't get it.
In all high pressure instrumentations, because I'm dealing with 300 bars and 350 degree centigrade, so in the reactors, so we always keep a minuscule rupture disk there, as Dr. Akbar rightly said, and of course you were explaining the similar
No,
things.
I was explaining actually a different thing, but now I got it what you meant. Safety, usually it's a safety valve or safety
Exactly.
disc that we use. Yeah, that's in our 2 meter crater have as well. Yeah.
Dr. Nazar, have you read through or got a chance to read through our marine process patent? The hybrid power generation for Mars. We have a supercritical water system in it, which has a temperature of 550 degrees Celsius and 300 bar. So when you mentioned you're dealing with 300 bar and 300, that looks like we have a synergy here. We'll talk about it because I've got no one to talk to with this type of pressures and supercritical water. Yeah, that's interesting.
Right. So second question that Dr. Nazair had was related to the charged particles. Maybe Akbar, if you want to take that and explain it through the AIRS that we will actually have when we build it on Mars.
So part of the Craterhab patent document has a patented technology on it that we have patented is the AIRS, Active Integrated Radiation Shield. Because the current models of radiation shielding is like 5 meters of regolith or 10 meters of water. That is not sustainable because that's very heavy structure and not safe from the safety point of view. So what we have developed or our design is an active shield made up of a liquid superconductor cooled by liquid nitrogen uh, that will create a non-ionizing radiation. that because of the superconductor, it will consume a few hundred kilowatts for a 200 to 300 meter diameter Craterhab, and that would be able to deflect up to 0.1 to 1 giga electron volt protons from the cosmic radiation, deflect away from the dome system. And because it is scalable, so we can always crank up the voltage in case of any high radiation event like solar flare. So that's our mitigation strategy for the radiation problem on Mars, because we think that humanity should go forward. We don't want humans to be living under underground cave systems or under thick regolith shield like mud houses. So we have created this or developed this radiation mitigation strategy, which is made of superconductors. And on Mars, it will work beautifully because the temperature on Mars is already low. So anywhere from -50 to -150 degrees Celsius. So superconductor would naturally work better. We don't really need a lot of cooling to make it work. So Martian environment is really designed is much more suitable for a superconductor based radiation shield. So the cables will be running through the skeletal frame of the dome, YBCO, superconductor, and liquid nitrogen. Any other questions? I think Rahul's mobile battery ran out as well, so he's now in complete dark, unfortunately. For him. Okay, just a couple of things to add. So, when you mentioned that using a crater for building the habitat structure is very advantageous, we use the term minimal material to volume ratio, or maximum volume to material ratio. So what is happening is that we are getting maximum volume out of the minimum amount of material, because we are getting, for the same amount of material to build a habitat system on flat surface, we're getting double the volume if we build it over a crater. So just put that in the presentations in the future, so that we can have proper terminologies for different aspects of the technology.
Note it down. Note it down.
All right. Any other questions? I asked, you have a question? Alejandro, you have a question?
Not from my side. It's all clear. I just would like to have later on that presentation, if it is possible for us to study the numbers, because it helps us to explain better, the testing procedure. The testing procedure, I believe, is pretty much helpful for us to attract investors. The testing procedure is key to understand the how does the feasibility of the technology. Okay.
One more question that can be asked is the safety from the drying effect of the Martian environment. Not much so on Earth, but for Mars. So in the patent document, you might have read about the word Kapton. So the entire dome would be covered in a very thin layer of Kapton or polyamide tape, which is actually very cheap. It's the same material that the visor of the astronauts when they do the EVA, the spacewalk, their visor is covered with this golden. You might have seen this golden reflecting surface. That's the Kapton, and that provides an excellent vacuum protection. So the entire dome would be covered in that. And in my drawings, actually, you might have seen this very slight golden tinge in all drawings. That's exactly what it is, and that's why in the background you see this golden ambience because of that Kapton layer outside the dome where I'm sitting right now.
Yeah, but I'm sure that there will be certain lighting ambience controlling mechanism inside as well, so that not everyone keeps thinking that we are in past. It's sepia color. So I think
in Mexico, this is Mexico. The Mexico filter.
Fair enough.
But I think then we should wrap up the meeting then. That has been our longest meeting at 2 hours.
Yep.
Right, thanks for the patience, and and the stamina of presenting.
I
Thank
would
you so
like
much for
to
joining.
I would like to thank everyone for the feedback, especially the questions that are asked and things that we have to focus on more. So that was very valuable. There are lots of things that Alejandro mentioned that we might need to have to work on and share more data related to the stresses, the individual stresses and forces. And of course, Dr. Nuzair's question related to safety disk and all that, we will have to, I think, incorporate that in the presentation as well. That what is the threshold for those safety mechanisms, so that we do not over pressurize in case there is a over pressurization by any reason for any reason. There should always be some safety mechanisms that will release that extra pressure out.
All right. Well, thank you so much for joining. So we'll end here and hopefully we'll meet again. Okay. Thank you so much. Thanks everyone.
Have a
Thank you
good
very
day.
much.
Bye. Thank you.
Bye.